Question 13. This is a multi-section type problem. With these types of problems, this is equivalent to the Section A, Section B problems that we had in kinematics. In fact, it really is just an extension of those Section A, Section B. Let's take a little closer look. A child pushes a 5 kilogram block from rest with a force of 7 newtons against a frictional force of 3 newtons. The child pushes the block for 3 seconds, and here's the key. Then let's go. The moment the child lets go of the block, the motion is going to change. This signals that we have now entered into a new section, or the Section B portion of the question. The rest of it, the block is allowed to stop on its own. What information does this give us? Well, we know that the beginning of our second section happens at the end of our first. And the same things are relevant. And that is, the velocity at the end of Section A is the same as the velocity at the beginning of Section B. And that helps tie things together. Therefore, in these multi-section problems, they are usually a combination of dynamics and kinematics. Let's continue. Part A, draw a free body diagram of the block during and after the push. And of course, you label them A and B. Determine the acceleration of the block during the push, the distance of the block as it travels during the push, and then the final speed, technically final velocity, of the block at the end of the push. Then you're asked to determine the acceleration of the block when it's sliding on its own, and the amount of distance the block travels when it's sliding on its own. Again, this is the whole idea of your Section A, Section B business. Let's focus on the givens now. The mass of 5 kilograms does not belong to one section or the other exclusively. It belongs to both. It's the same mass. So we don't have to put that under Section A or B. It's just the single mass. In Section A, however, here is the list of both dynamic and kinematic parameters. We know that we have the force of the push, and it's 7 newtons in the forward direction. The force of friction is 3 newtons in the reverse direction, or the back direction. VA1, we're assuming, is 0 meters per second. Not assuming, I should say. It did say explicitly starting from rest, so that's not an assumption, that's actually a given. And the time for Section A was 3 seconds. And as stated up there, the child pushes the block for 3 seconds. That is associated with Section A. Then in Section B, the push force is now gone, but the frictional force remains. And we should probably put our little direction there. There we go. And we know that the final velocity at the end is going to be 0 meters per second. And as you can see, I have a note that VA2 equals VB1, which is the property of Section A, Section B. Under required to find, we're looking for the free body diagram during the push and after, the acceleration during the push, displacement during the push, and acceleration and displacement post-push. So let's take a look at the free body diagrams. So during the push, note that we have FP, force of friction, normal, and gravity. But what I don't have are any extra subscripts. And the reason being is that we don't have 2 objects. It's 2 different sections. So the mass is the mass, which means the normal force will be the same and the force of gravity will be the same in both cases. The only difference here, and as you can see, these are the same vectors as before. The only difference is that in Section B, we are missing the push. Part B, we need to find the acceleration in Section A. Now, again, as a reminder, acceleration is either a kinematics thing or a dynamics thing. So basically, you need to take an inventory of what you do or do not have and see which approach is going to work for us. So let's start off with just seeing if we can use kinematics to solve this. So we have the 5 kinematic parameters. And so far, we only have the following pieces of information. We know what VA1 is, and we know what the time is. That's only 2 out of the 3 necessary pieces of information. We're trying to find the acceleration. That's not nearly enough. We would need either the displacement in Section A or the final velocity in Section A, and we don't have those. So therefore, what we're going to do is we're going to look to the dynamics. Now, in this case, what you're going to notice, I only focused on F net AX, making my life a little bit easier here, and hopefully yours as well. If we look at the diagram, we know that the Y components cancel each other out. So the Y components don't contribute to the acceleration. So in Section A, the acceleration in section A in the y component is equal to 0 meters per second squared. And that's the not floating or sinking business. And the same thing, of course, applies in section B as well. So the acceleration in section B in the y component is also 0 meters per second squared. In section A, the x component of the acceleration, even though we don't know what the value is, we know that it's going to be in the positive direction. And that's because Fp is greater than the force of friction. And we should use the proper subscripts. There we go. And in section B, the x component of the acceleration, and didn't exactly give myself enough real estate there, will be in the negative direction. There we go. Okay, so note, the x component of the acceleration is just equal to the acceleration in section A. And the same thing applies in section B. So focusing on the x component only, we know that the net force in section A along the x is equal to Fp plus the force of friction. Dropping the vector notation and using Newton's second law, we know that the net force is equal to ma. So in this case, it's going to be mass times the acceleration in section A. Notice there's no subscript on m because it's the same mass in section A and section B. The thing that's different is the acceleration. And that's why I have a subscript A on the acceleration. The push is positive, the friction is negative. We isolate for the acceleration by removing the factor of mass through division. Substituting in, we get an acceleration in section A of positive 0.800 meters per second squared, or 0.800 meters per second squared in the forward direction. Positive as expected. Now for part C, we're asked to find the distance/displacement in section A. Now we do have enough kinematics information to solve the rest of the unknowns. As you can see, we have our VA1, our time in section A, and now of course we have our acceleration in section A, but it is subject to potential error, hence written with the amber color. But we have no choice, so we have to use it. Since we're trying to find the distance in section A, we have to use the one formula that does not have VA2 in it, and that is equation number 2 in our accelerated motion. D is equal to V1t plus 1/2 AT squared. Substituting in, we end up getting 3.6 meters. Therefore, dA is equal to 3.6 meters forward, except let's get the proper number of sig figs. All right, that's better. Part D, we're looking for the final velocity in section A. And let's go back to our list here. So now, since we are looking for our VA2, we technically have the remaining 4 things. Now, this displacement in section A, I'm going to give it a check mark, but I've made it even dirtier than the acceleration. Why is that? This is because dA is based on this accelerated value. So what that does is gives us the potential to even have more error in our calculations. Doesn't mean that we do, it just means there's even greater potential. So we want to get as pristine as possible. Therefore, we should avoid using dA to calculate our VA2, which is what we're going to do. We're going to avoid using dA, which means that we have equations 6 and 7 to work with. So VA2 is equal to VA1 plus acceleration A times the time in section A. Substituting in, we get 2.4 meters per second, or I am all over the place with my sig figs. Good gravy. All right, let's fix this up. 2.40 meters per second forward. But we also now know that our VB1 is equal to 2.40 meters per second in the forward direction. So we have this new information that will help us with the second section. Now here we go for part E. We're looking for the acceleration in part B. But as you can see, we only have 2 pieces of kinematics information. We have our VB2, which is a green given because that was given from the beginning. The 2.4 meters per second, which is amber, of course, because that was calculated. And we're trying to find the acceleration. Again, insufficient information from a kinematics perspective. That means we look to dynamics. And the same argument before, we really only care about what's happening in the x component, because when we look at the free body diagram, Fn and Fg just cancel each other out anyway, and all the acceleration is happening along the x-axis. But in this case, we have only the force of friction acting, and the friction is working in the negative direction. So when we isolate for our acceleration in section B, we divide that force of friction, that negative force of friction, by the mass, and we get a value of negative 0.6 meters per second squared. And the negative makes sense because we know that it's going to slow down. So therefore, our AB is 0.6 meters per second squared backwards. Now we have 3 known values. And as a result, we can now find the remaining kinematic parameter that we're looking for. We're looking to find the displacement in section B, or the distance. And we have VB1, VB2, and the acceleration. Of course, VB1 and the acceleration were both calculated results, but we have no other choice, so we have to use that. Therefore, we're using the one equation that doesn't have time in it, which is, of course, our equation number 5, which is VB2 squared is equal to VB1 squared plus 2AB dB. So isolating for D, again, using SAM, DEB in reverse, we have our 3 terms. This is our term of concern. So bringing VB1 squared to the other side makes it negative. Then we have our term by itself. Obviously, next step is we have to remove the factors. So we have to remove the 2AB. They're attached through multiplication. The opposite of multiplication is division. So we're left with dB is equal to VB2 squared minus VB1 squared over 2AB. Substituting our values in, we end up getting 4.8 meters. Therefore, our dB is 4.8 meters in the forward direction.